Okay, so let's look at this proportion problem. And let's notice that since there's a p instead of a mu, this tells us proportion. Okay, so I'm going to write down, first of all, that our alternate is p is greater than 0.19. I have a sample size of 462, so that's large. And there are 95 successful observations. 95 observations. Okay. Um, so you should use a normal distribution, blah, blah, blah. And alpha is 0.005. So we want to find the test statistic and the p-value, and of course, go through the rest of our hypothesis test. Okay, so first, let me pull up our formula sheet and let's pay attention to this right here. All right, so our formula, and I think it'll just let me copy it to another page. So let me do that. Okay, so probably one of the problems you're having is that you're not spotting what p hat is. All right, so let's talk about the proportion p hat. So our sample proportion, let's get that. Let me go back to draw here. All right, so to find p hat, let's notice in the example we had, there were 462 in the whole sample, and there were 95 successful observations. So our sample proportion is the 95 successful observations over the 462 in the sample. So 95 divided by 462 is 0.20563. No, my 0 and my 6 don't look very, there we go. All right, now let's notice that we've got to find our sigma hat first, and that's going to be our p, which we had in our null hypothesis, was 0.19. And Q is always 1 minus 0.19 or 1 minus P. So it's going to be 0.81, which is what we get if we subtract 1 minus 0.19. And then our N is 462. So I'm going to put all of that into the calculator at once. The square root of 0.19 times 0.81 divided by 462 ends up being 0.01825. All right, now let's fill in our test statistic. P hat is the 0.20563 that I got before. P is from our null hypothesis, it's 0.19. And then our sigma hat on the bottom is 0.01825. Okay, so let's do the top calculation. Let me kind of scroll this down if I can. It's not letting me move things down. Okay, so when I subtract the top, I get 0.01563. And of course the bottom is still the same. And when I divide that out, I get a test statistic of, and it's said to round to 3 decimal places, so 0.856. All right, now we want to look up 0.856. Remember, this is my z-value, so when I go to Excel, I just want to use my norm.s.dist, put that in, and see what the corresponding p-value is. So let me see if I can go to my Excel. All right, so equal norm.s.dist. Our z-value is 0.856, true, and the corresponding p-value is pretty big, 0.804001. All right, so if we look back at our problem, the p-value would have been 0.804001, which is in no way, I'm sorry, it's a greater than, so we have to subtract that from 1. So let me just do that on the Excel page. So equal 1 minus 0.804001, and that is 0.196. Now, 0.196 is in no way smaller than 0.004. It's greater than alpha. And of course, that means if it's greater than alpha, we failed to reject the null. So we do not reject the null. And so there's not evidence to support our alternate. So there's not sufficient evidence to support the claim that the population is greater than 0.19. We can't support that alternate. Okay, so hopefully that helps with these proportion type problems. And remember that the p-value, the process defining the p-value is the same. It's the test statistic that is different. So if it's a greater than, we'll look it up and subtract from 1. If it's a not equal to, if our test statistic is positive, we will look it up, subtract from 1, and then divide by 2. If our test statistic is negative, and this is a not equal to, we will look it up and divide by 2. And if this alternate is a less than, we just look up the p-value once we have our test statistic. So hopefully that helps.